Hello, Yash.
Yes, ma'am.
Yeah, happy Independence Day.
Thank you. You too, ma'am.
Yeah. So we will wait some more students to join, then we will start it. Okay.
Okay. For a while, I have one doubt. Can I ask, ma'am?
Yeah. Yes. Yes. You please.
In your assignment 3, I have one query that isentropic efficiency is not getting that value in option.
Okay. You're not getting the value what it is given in the option, right?
Yes, yes.
Yeah. Okay.
I,
Do.
I got 90%, but there is no option. But,
Oh. Okay. Okay. That I have to discuss with them. Like one more, two more TAs are there from that professor side. Okay. So do one thing. You please give comments on NPTEL discussion forum. Did you do that?
what, ma'am?
Did you discuss this in the NPTEL platform?
No, ma'am. I have not discussed that.
Okay, okay. So I will discuss with them and give you that. Okay, reply for that.
Okay, no.
Yeah. You will wait 2 more minutes, then we'll start. Okay, so we'll discuss we'll start to discuss now. Okay, like I think if others join, let they join by that time. So we will start our discussion. Um, so as I discussed last class, we discussed only the problem parts, like what will be in the mathematical part. So today we'll discuss few theory part, like theory kind of questions, and as well as the problem part also. I hope you can see the question. So it's continuation from the last class. So here, the first question is the expression of closed integral delta q divided by t is equal to 0 is true for option A, reversible process only, and option B, reversible process only, option C, reversible cycle only, option D, Carnot cycle only. So for this question, anyone can answer for this. What will be the answer?
C option.
Option C.
C.
Yeah, it's only for reversible cycle only. So now let us move to the next question. The reason for irreversibility. So options are heat transfer with finite temperature difference, fluid friction, mixing of two fluids, all of the above. What will be the answer for that? The reason for irreversibility.
All of above.
Yeah. Yes, correct. So heat transfer with finite temperature difference. That also is reason for irreversibility, and fluid friction. If friction is higher, then it will be like irreversible, and a mixing of two fluids. All are the answer for this. Okay. Now let us go to the next question. Heat transfer process in a Carnot cycle will be options are isobaric, isochoric, isothermal, isentropic, that we already discussed about the Carnot cycle in two classes. So the answer is C, isothermal process. Now next one is free expansion is an reversible process, irreversible process, work producing process, and work absorbing process. So the answer will be irreversible process. Free expansion is an irreversible process. These are like normal basic theory questions. Now, if we go to the next one, the second law, efficiency for power and refrigerator cycle, is lies between 0 and 1 minus T low divided by Ti, the T is temperature, and lies between 0 and 1, lies between 1 and infinity, none of the above. That's also we discussed last class when we discussed about the second law and solving one problem that time. So it's only lies between the 0 and 1. So the efficiency for a power and efficient for power and refrigerator cycle will be between 0 and 1. Now if we go to the next problem, due to the action of atmospheric pressure, the available useful work means expansion here we are discussing, it will be increasing or decreases or remain unaltered and cannot be determined. So answer will be decreases. So due to the action of atmospheric pressure, the available useful work decreases. Okay. Now, next one, the required reversible work is in the case of work absorbing device is greater than the supplied actual work, is less than the supplied actual work, equal to the supplied actual work, or none of the above. So what will be the answer for this? Anyone can say for this?
B
That's,
option.
yeah,
Yep.
answer is B option. The required reversible work in case of work absorbing device is less than the supplied actual work. Okay. Now these are the basic theory questions, and you can see this in your assignments also. I think previous assignments it will be there. So these are the answers for that. Now we will discuss the problem for this last assignments. Okay, no, this is not exactly same problem, similar kind of problem. Exactly same problem I'm not discussing here. That's if you like try to understand this kind of problem, then you can solve that kind of also. Okay. So first question, the problem section. What will be the loss of available energy associated with the transfer of 100 kilojoule of heat from constant temperature system at 600 Kelvin to another at 400 Kelvin when the environment temperature is 300 Kelvin. The options also given here. A option 150 kilojoule, 250 kilojoule, 500 kilojoule, 700 kilojoule. Okay. So the question once again I will tell, what will be the loss of available energy associated with the transfer of 1000 kilojoule of heat from a constant temperature system, from a system at 600 600 Kelvin to another at 400 Kelvin. So heat transfer is happening, means energy is transferring from 600 Kelvin to 400 Kelvin, and the environment temperature which is given at 300 Kelvin. So you have to tell what is the amount of energy loss here. Okay. So for that finding, you can calculate loss of available energy. That you can write as T0 ds2 entropy by 2 second system minus ds1, that you can write it as T0 times entropy, we can write it as Q by T2 minus Q by T1. So this is the formula for loss of available energy. Now what you have to give here, temperature already given in Kelvin, so no need to convert into any other dimension, like, so you have to write that T0 value is 300, that is environmental temperature, and Q is already given 1000 kilojoules, so 1000 divided by T2 is what, first one, mean second one, it will be 400, so 400 minus 1000 divided by 600, and you have to solve it now. Can you please solve and tell me the answer for this question? Which option will be the correct one? So everyone try this and please let me know the answer for this.
Two fifty.
Which option?
250.
Yeah,
B option.
yeah, B option. We will wait 2-3 minutes to others also solve this, and we'll go to this next problem in that. So I will explain once again what will be the loss of available energy associated with the transfer of 1000 kilojoule of heat from constant temperature system at 600 Kelvin to another at 400 Kelvin when the environment temperature is 300 Kelvin. Okay, so here what we have to use the formula loss of available energy, that will be T0 means environmental temperature and times ds2 minus ds1. It will be T0 times Q by T2 minus Q by T1, and we have to just substitute those values here. It's already given all the values. So 300 times 1000 divided by 400 minus 1000 divided by 600. So the answer will be 250 kilojoule. Okay. Now we will go to the next problem. The next problem is 1000 kilojoule per second of heat is transferred from a constant temperature heat reservoir maintained at 1000 Kelvin to a system at a constant temperature of 500 Kelvin. The temperature of surrounding is 300 Kelvin. The net loss of available energy as the result of heat transfer. Okay, so you have to, it's also similar kind of question. You have to solve it. So first the question, once again I will read it. 1000 kilojoule per second of heat is transferred from a constant temperature heat reservoir maintained at 1000 Kelvin to a system at a constant temperature of 500 Kelvin. The temperature of the surrounding is 300 Kelvin. The net loss of available energy as a result of this heat transfer is. So here option I didn't give. You have to solve and find the answer for this. That okay. As like earlier problem, here also what you have to find, you have to find the loss of available energy. So that you can represent as So first here we will find what is the delta as well, change in entropy. Okay. So in the change in entropy case, heat is already given here also. It is 1000. So 1000 divided by 500 minus 1000 divided by T1 is 1000. So the answer, how much will be the answer for that 1000 divided by 500 will be 2 minus 1, the answer will be 1. So the answer is 1 kilojoule per Kelvin second. Okay. Now if we discuss, we have to find the available energy, total available loss of available energy. For that, means energy will be T0 times this one. So T0, what is the T0 value here? 300 Kelvin, that is the temperature of the environment or surrounding. So 1, it will be 300 kilojoule per second. So this will be the answer. So I can repeat the question once again. 1000 kilojoule per second of heat is transferred from a constant temperature heat reservoir maintained at some of you already answered in the chat box. Now I check that. So I will explain once again for others. Then we will go to the next problem. Okay. So normally in this kind of problem like heat, you have to find the loss of available heat. Such case you have to use the formula. This one, loss of available energy is equal to T0 times delta S. Delta S is the delta S is the change in entropy in the system. Like when temperature changing from T1 to T2, what will be the change in entropy? That is delta S. So for normally you have to find the delta S value first. Then you have to go multiply it with the normal surrounding temperature or environmental temperature. That is the normal terms will be given in the question also. Then multiplied, you will get the answer. So here in this case also it is given that like T1 is 1000 Kelvin and T2 is 500 Kelvin. Okay, this one. So then heat is given, it's already 1000 Kelvin. So what you have to do, substitute here in the delta S. You will get the answer 1000 divided by 500 minus 1000 divided by 1000. So it will be 2 minus 1. That is 1 kilojoule per Kelvin second. Now what you have to do, you have to multiply it with loss of available energy to find that. So what you have to multiply with T0. T0 is the surrounding temperature, that is 300 Kelvin. The answer will be 300 kilojoule per second. Now we will go to the next problem. So next problem is air in a closed vessel of fixed volume 0.15 meter cube exert pressure of 12 bar at 250 degrees Celsius. If the vessel is cooled so that the pressure falls to 3.5 bar, determine the final pressure, heat transfer and change of entropy. So here you have to find three parameters. One is final pressure, and another one is heat transfer, and another one is change in entropy. Okay. So first let us see what are the parameters given here. So volume, which is given, so we can write it as V1 is 0.15 meter cube. Okay. Now exerted pressure 12 bar, right? So we can write P1 is 12 bar and P2 is how much it is given, 3.5 bar. That you have to convert it into normal in Newton per meter square. So if you convert 12 bar into Newton per meter square, it will be in kilonewton per meter square. Similarly, it will be 350 Newton per meter square. Okay, so that is the parameter which is given. Now, from the ideal gas, like in earlier classes, we learned that from the ideal gas equation, you can find the mass of the system. Mass, what it will be. P1 V1 divided by RT. Okay. So substitute the values here. P1 is already given, V1 is given, and R we know already the value, and P1. Substitute it, and what the answer you are getting, please let me know. And here one thing you have to remember, you have to change the temperature to 50 degrees Celsius into Kelvin. That also you have to remember. So if you convert 250 degrees Celsius to Kelvin, it will be 523 Kelvin. So if you substitute all this P1 and temperature R and B value, you will get the answer 1.2 kilogram. Okay, so the mass will be 1.2 kilogram. Now what we have to find? We have to find the final pressure, heat transfer and change of entropy. So first we will find final pressure. Okay, to find the final pressure, you can write like here already the pressure is given, small change in the question. You have to find the um, final temperature that you can get like T2. T2 will be what? T1 times P2 divided by P1. So here already T1 is given, P2 and P1 is given. Please find the answer for this. Okay. Substitute the values here. So T1 is what? 523 times P2 is 3.5 divided by 12. And what will be the answer for this? The answer for this question will be 152.54 Kelvin. So just let me explain this question once again. You have to find the final pressure, heat transfer, and change of entropy. So there, air question is air in a closed vessel of fixed volume 0.15 meter cube, exert pressure of 12 bar at 250 degrees Celsius. If the vessel is cooled so that the pressure falls to 3.5 bar, determine the final pressure. Okay, I mean not final pressure, final temperature and heat transfer and change of entropy. So in such case, first we will write what are the parameters is given. So here volume, fixed volume V1 that is 0.15 meter cube and pressure P1 that is 12 bar. That is, we can, if you write into kilonewton per meter square, it will be 1200. Now P2 that is 3.5 bar, that you can write at 350 kilonewton per meter square. Okay. Now first before going to that, we will find the mass of it. We need mass for some other for calculating change of entropy and heat transfer. For before going to this section, we will find the mass also. From Ideal's equation, you can get the mass is equal to P1 V1 divided by RT1. Now, for solving a temperature in degrees Celsius in a problem, what you have to convert? You have to convert degrees Celsius to Kelvin. So, 250 degrees Celsius you can convert it into 523 Kelvin. Then substitute here, you will get the answer 1.2 kilogram. Okay. Here P1 value is what 1200 you can give. V1 is 0.15 divided by what you will get 12 divided by the R value is 0.287 times 523. Then you will get the answer 1.2 kilogram. Okay. Now we will go to there are three questions. You have to find the final temperature, heat transfer and change of entropy. To find the final temperature, that is T2. T2 you can get as T1 times P2 divided by P1. So everything is given here. So 523 times 3.5 divided by 12, you will get the answer 152 times 54 Kelvin. Okay. Now we have to find two more parameters. So for that, next one what you have to find? You have to find the heat transfer. So for heat transfer, Q is, you can write it as mCp times T2 minus T1. Okay, so here we need the mass NCP value and T2 minus T1, like temperature temperature, that is change in temperature. So it will be 1.2 times Cp and constant pressure. It will be 1.005 times 152.54 minus 523. So if you calculate this one, so first you try the answer, then please let me know what will be the answer. Then I will tell the answer here. It will be a negative value because 152.54 minus 523 will be a negative value.
Hello, Aishwarya. I'm
Yes.
interrupting you. Sanju is there. He's asking, or C, I do not know. He asking to repeat the R value, how you have decided. The value of gas constant. Please repeat it for him.
Okay. The R value which I took is 0.284. Yeah, like these R value for when we are converting to bar, because we are problem considering if pressure is in bar, then we have to give the R value accordingly. Whatever we know 8.3, that is for normal SI unit. So here pressure is R on bar, that's why I took it as value for 0.284. Okay, so yeah, in chat box, yeah, that answer minus for 44.78 joule, that is correct answer. And okay, the normal formula for heat transfer is QCP times delta T, right? Like mass flow times specific heat capacity and temperature. So that's why here also I use the same, like CP, for solving the problem.
But ma'am, the process is a constant volume process, right?
Yeah,
How will it give the correct heat transfer in this process if you are not using a specific heat capacity or constant of a constant volume?
it's CP, right?
CP is specific heat capacity for constant pressure.
Yeah,
But the process is a constant volume process, so shouldn't a CV be used for the calculation of heat transfer?
okay, I will use.
Aishwarya, can you go to the previous slide where we can
Okay,
read the
the
question?
question, yeah, yeah.
So as per question, uh, Rima is right, I think. We should use CB, 0.718 kilojoule per kg.
Okay, 1 minute, let me check that.
Hello.
Yeah, actually, for in compressible case, CP will be equal to CB. Okay.
Hello.
Yeah.
Yeah, Miss Rima, you have rightly pointed it out. So, means like the value will be given for your reference in the question itself. Okay. So the CP and CV values they will be provided to you, and you have to use the value accordingly to arrive to the final answer. I think you have, Miss Rima.
Yes, I can hear you.
Yeah, yeah. Are you getting it now?
Yes, but I
Yeah.
wanted to ask in this question, CV will be used only, right?
Yeah, yeah. It will be used. It will be used because it's
Okay,
a constant
thank
volume
you.
process. Yeah, yeah.
Thank you.
So that will be used and it will be provided to you, or otherwise, if we are saying that it is an ideal gas process, if we are considering air to be the ideal gas, then accordingly you can find it out
Okay,
on
okay.
your.
Thank
Yes,
you.
yes. Okay, thank you. Aishwarya, you can continue.
Yeah.
Yeah.
Okay, here the answer is minus 446.78 kilojoule. Okay. Now, next one, what the casting question? Change in entropy. So, change in entropy, you can write delta S is equal to m times Cp log T2 divided by T1 minus, like in the case it will be same. So, Cv you can write it as minus R log P2 divided by P1. Okay, so here the all values are available. So mass will be 1.2 times the value 1.005 times log 152.54 divided by 523 minus 0.284 times log 3.5 divided by 12. So you have to find the answer for this. So answer will be minus 1.06 kilojoule per Kelvin. Yeah, so these are the questions. So I want to discuss with you. So this kind of one more question I will discuss in next class to clear more clarification on this. Okay, like, and I will try to explain the CPCV part also, like for what are the CPCV, like when it will be less than, when it will be equal, and when it will be higher. So that part also I will try to explain, and will try to solve more problems on this area. And one more thing, another, like whatever problem we discussed, these two are like already assignment problem. You can see same kind of problem. That's why I solved two similar kind of problem with different values and options. So I think these kind of problems you can see in your week two assignments. I think so. We will wind up here today. So we will meet next Monday.
Thank you, ma'am.
Yeah,
Thank you, ma'am.
yeah, yes, yes. You can leave now.